at graphing logarithms, and we're going to use the concept that we started with, where we're talking about logarithmic functions and exponential functions being inverses of each other. So let's do one here where we've got a base 2 situation. So since they're inverses, let's do one that's pretty simple. Let's do 2 raised to the x. So we'll use this exponential function first. So if I raise 2 to the negative 3, that's the same as 1 over 2 to the third, or 1/8. And I gotta make a switch here. So that's 1/8. So I've got negative 3 and positive 1/8. So a pretty small value there. Negative 2. 2 raised to the negative 2 is the same as 1/2 to the positive 2, which is 1/4. So now right around here. If I do negative 1, 2 raised to the negative 1 is the same as 1 over 2 to the first, or 1/2. So now we're right there. 2 to the 0 is 1. If you remember back to exponential functions, 0, 1 is kind of an anchor. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So we get something that looks similar to that. Now remember, this is old. This is our exponential graph. And again, this was going to keep going this way. And remember, our x-axis actually is an asymptote for that. So there we go. Now since we're talking in terms of inverses, remember our inverse just means we're going to flip-flop our x and our y. So we're going to take each of these, I'm going to flip them. So now when x is equal to 1/8, y is going to be negative 3. So we're going to be way down here and very close to the y-axis. When x is 1/4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0. When x is 2, y is 1. And when x is 4, y is 2. And when x is 8, y is 3. So now this time we get a picture that looks something like this. And this time our y-axis becomes an asymptote. Now again, if we look at our values, and let's look at just some of these positive values here, we had 0, 1, we had 1, 2, we had 2, 4, we had 3, 8. Now if you look at what happened on our graph down here, we just turned them around, and we actually just ended up with, out here, 8, 3, 4, 2, 2, 1, 1, 0, and so on. So they just ended up mirroring each other. And of course, where that mirror is, we've talked about this in previous chapters, that mirror is actually coming from our inverse. And anytime we have an inverse, it's going to mirror itself. Make sure you get the right line here. That mirror is the equation, or the line y equals x. So that's our line of symmetry. So these are the same distance from each other. These are the same distance. So the distance from this point to our line of symmetry is equal to this. This point to line of symmetry is equal to this, and so on and so on and so on. So you might want to start by just finding your exponential function, flipping all the x's and y's, and letting that draw out into your logarithmic function. So pretty simple way to find the graphs use the exponentials. Now, some of our shifts, whatever we've done in the past as far as transformations go, it's going to work the same way now. So let's say we've got this as a beginning or a start point here. F of x equals log of x, so we'll just go common log. If all of a sudden we throw this at you and say find g of x and graph it if it's this, log of x minus 1. So we're going to use the same concepts that we've used before, and in this case it's involved inside parentheses with the x, so we're going to think opposite, and we're just going to take that original graph for log base 10 of x, whatever that picture is, and we're going to take this and we're going to move it right 1. So all the x values get 1 bigger. If we were to look at one that looks like this, 2 plus log of x. Now it's outside the realm of the x, and it's just 2 added onto this, so the y value is going to get affected. That's going to tell us that we're going to move everything up 2 units. In other words, all the y values end up doubling. So, pretty simple concept there. So whatever shifts we've done in the past, the same shifts are going to happen now. Let's look at one more here. Let's do k of x. Let's say we just do negative log of x. Well, since that's on the outside, it's going to affect the y, so all the y's get multiplied by negative 1, so that's just going to be a reflection over the x-axis. Now, same thing if it happened on the inside. Let's say we've got log of negative x. Since it's on the inside, it affects the x's, so they're going to flip, which means we're going to get a reflection again, but this time our reflection is going to be over the y-axis. So again, all the concepts that we've done before, and there's others as well, but these were some of the main ones, nothing's going to change. That'll be the same as what we've done before. Okay. Now, we've talked about common logs being base 10. We also have another special one that's used quite a bit, and another one that the calculator can help you out with, and it's called natural logarithmic function. So natural logarithmic, and I'm having trouble writing here tonight. Natural logarithmic function. In other words, that's going to come with base e. So I could write something like this, log base e of x, but again, since this is another one that's used quite a bit, it has its own notation, which is ln. So anytime you see ln, it means log base e. Now all the concepts that we've talked about before, everything's going to be the same, and again, this is an inverse of our exponential or natural exponential function e to the x. So everything we talked about with logarithms, same thing comes back, it's just base e is another special type that gets used in quite a bit of application. Right. Now the other part of this, same as we did before. That's got to be a positive value. I can't raise 2.71828 whatever to any power and get a negative solution. So all the things that held before hold the same now, as well as you would think. The properties, same thing. Natural log of 1 is 0 because e to the 0 power equals 1. Natural log of e equals 1 because e raised to the first equals e. Third property that we used before was when we had an exponent, but we had a base matching the number here. So here e of e, this is just going to give us the exponent. And remember, this was one also where if we had a value where the logarithm was in the exponent. Well, here's base e. Natural log says this is base e. Whatever this value, in this case x, that becomes our solution. And then the fourth property, same as we did before. Natural log of x is going to equal natural log of y if x and y are the same as each other. So everything we've dealt with before is going to still work the same way as what we did in the past with other logarithms. It works the same with natural logarithms. So you can look back at some of the examples that we did for the logarithms if you need to. It's just a different base that we're using here is all. All right, one last thing to look at in this section, and that's dealing with domains. So our domains of logarithms, again, think in terms of horizontal shifts or reflections. So if we were going to just go with, since we were just talking about natural logs, let's do one of those. So if f of x equals natural log of x minus 2. Well, when we drew our regular logarithm, if you can think about this, if I was just doing natural log of x, remember it's going to take on generally a shape like this. It's going to go through 1, 0, and it's going to have my y-axis is my asymptote. So remember, this tells me, hey, everything's going to move to the right 2 spots, including my asymptote. So if I go to the 2 to the right, that's telling me that my domain is going to be all x's greater than 2, because we can't touch that vertical logarithm. So in terms of interval notation, we would say 2 to infinity would be my domain. Now, another way to look at this, let's look at a different problem here. Let's say that they give us a g of x equals natural log of 2 minus x. Looks fairly similar to the one we just did. But a couple things are happening. Now, we can go through all our shifts and everything like we did here, or we can go back to one of the things that we talked about earlier. We know a logarithm or a natural logarithm has to be a positive value. So one shorter way is take that value, in this problem, 2 minus x, and set it greater than or equal to 0. In other words, positive. So I could add my x over here, and I'm going to get 2 greater than or equal to x. So if I were to do this, I'm going to end up with, oops, and I got to make one change here. It's going to be just greater than. It can't be equal to. It's going to be greater than. So 2 greater than x, or x less than 2. So on this one, it would be going from negative infinity up to 2 would be my domain. So just a little something to be careful of when you're working through some of these problems.